Good morning, class. I'm sorry I couldn't be in the class today, so I will record today's lecture and upload that on my YouTube channel. I will give you the link. Just to start, we discussed the static pressure variation in horizontal direction, and we found that in horizontal direction the pressure variation was 0. That means at any point the pressure will be same. Now we will start to discuss the static pressure variation on vertical direction. I think for 2 sections I already completed that, and for 1 section I couldn't complete that. So I will start from the very beginning for this part, so that for which class I already completed you can do a very quick review. So for the vertical direction, the only difference with the horizontal direction is we have one extra force component, which is actually the weight of this fluid column. So why we are actually writing gamma something instead of weight? So let's start from the specific weight, which is weight over volume. So weight will be gamma times volume. Now for this tube, this is the cross sectional area delta E, and this is the height delta Z. So basically the volume will be delta A and delta Z. Okay, and that's what they wrote here, delta A dz for volume. Now for this one we will use the conventional sign, which is the upward direction is positive. So from your statics class, if I say Fz in upward direction it's positive, it's 0 for the equilibrium. Now if I say this one is F1, this one is F2, and this one is W. So it will be F1 will be positive, F2 will be negative, and W will be negative also. So if I write down P delta A, this is the F2, and if I just remove the parenthesis, the final thing will be delta A dP dz delta Z delta A, and the weight of this is gamma delta A delta Z equals to 0. Now I can cancel these two. Finally I will have this one, negative gamma delta A delta Z. Now if I move one of this term on the right side, it can be delta P delta Z delta A delta Z. Now on both sides I have delta A and delta Z, so I will cancel these two. So finally I have dP dz gamma. So you can see, unlike the horizontal direction, in vertical direction we actually have pressure variation, and that depends on the delta Z. Now if you notice the negative sign, just to explain that sign, we assumed that Z is positive on the upward direction, and here we are seeing that P is like the P variation, it is actually happening with the negative Z direction. That means if you go in downward direction the P will increase, or if you go the upward direction the P is decreasing. That's why the negative sign. So what I will do, I will just write down this way, that if we go downward direction, pressure will increase. And you can imagine that, like, obviously the more you will go downward direction, that means the more material will be on top of some, like, a specific point. So obviously the pressure will be higher at that point. So that is the relation. And the pressure variation depends on the Z, which is the depth, and the gamma, which is the specific weight, which is one of the fluid properties. So based on these two, we can calculate the pressure variation in vertical direction. Okay. Now the equation we have there, that was actually for like compressible, incompressible both. Now we want to find out what will be the explicit expression for incompressible fluid, and then we will try to find out what will be the pressure variation for compressible fluid. So that's what we will do as a first step. We will do for the incompressible fluid. So the characteristics of the incompressible fluid is that it's unable to compress. That means you can't change the volume, and that means the gamma is constant here. Okay, that is the characteristics. And the example of incompressible fluid is water or any kind of liquid. Okay, so the expression we just got here from our previous slide, that was change of P or pressure is gamma. Now we told that the negative sign indicates that the downward, if we go to the downward direction, it will be positive. So what we will do, that's what we will use here, because this time we will use the Z scale in this way, like in downward direction. So I will just modify this equation into dP dZ gamma. Okay, so downward direction. Now from this point, what I will do, gamma dZ. Okay, now just think about this way. This is one particle, any single particle. Here, if we start the scale Z from here, obviously on top surface, the pressure is P naught and Z is 0, and here pressure is P and Z is H. Okay, so if I integrate that, just use this sign. Now for incompressible fluid, we already discussed that the gamma is constant. If something is constant, from the integration rule, we can say that that should be out of the integration sign here. Okay, now the next thing here, the limit. If you look at this particle here, okay, so it is actually in H depth from the surface. So, and we started our Z axis from the surface. So at Z, the pressure is P naught and Z is 0, and at this specific point pressure is P and Z is H. Okay, so then what I will, if you remove the integration or if you do the integration, it will be P minus P naught gamma H minus 0. So P equals to gamma H plus P naught. Okay, so that is the expression for pressure variation for incompressible fluids. That means for any liquid. Now, one thing here, this is the water surface, top of, or any liquid surface. On top of that, this is actually air. So the pressure exactly at that point is the atmospheric pressure. So P naught equals to P atmospheric pressure. So if we use the gauge scale, like for gauge scale, we know for gauge scale P atmosphere equals to 0. And if we use the absolute scale, P atmosphere will be like P atmosphere, atmospheric pressure depending on the scale. It can be 101.3 kilopascal or 14.7 psi, or it can be anything in other unit, mainly the value of the atmospheric pressure. So now we know, depending on the gauge scale or absolute scale, we can have the different value for P naught. But as I said, unless I state otherwise, obvious, always we will use the gauge scale. So most of the time we will see we are using P atmospheric pressure equals to 0. Okay. Now once we know that, one more thing. So for gauge scale, we just discussed that P equals to gamma H. Okay. Now, if you rearrange these equation, P over gamma, that is H equals to P over gamma, this P is actually called the pressure head. The pressure head means the height of a column of liquid that produces the gauge pressure P. That means at this point the pressure is P. This amount of liquid column is creating this pressure P, and this one is called the pressure head. Okay, so height of the column of liquid that produces the gauge pressure. Notice that word, the gauge pressure, because for absolute pressure there will be P plus P, P equals to gamma H plus P atmospheric pressure, so we can't do that. So this relation is true for gauge pressure. Okay, now once we know for compressible fluid what will be the pressure variation and what is pressure head, obviously our next task is we need to do some mathematical problem. So let's start the class example 5. So for class example 5, since there is no one here to read the question, I will read the question loudly so that everyone can hear. So the class example 5 said, find the pressure at tank bottom, ignore the weight of the tank. So this is a tank. This can be circular tank or rectangular. I think it's circular because that is the common shape. Though since they said that ignore the weight of the tank, I'm not worried about the shape of these things, and they are asking you to find what will be the pressure at this point. Okay, and for each we have actually 3 layers here: water, oil and air. For air, you are seeing the pressure is 150 kilonewton per meter square. So that is greater than the atmospheric pressure. That indicates that this is a closed lid tank. Otherwise, it would be just 101.3 kilopascal. Okay, so that's what they are asking. Just a few minutes ago, we learned that if you go downward direction, the pressure will increase, because we can explain that using this example. At this point, the pressure is only due to the air. So, like the pressure due to air. At this point, air plus this oil. And at PC, the pressure is actually pressure due to air, oil, and water. You see, the more we are going downward direction, the more material is added. So the pressure will increase and we need to find that pressure. So let's start working on that. And let's calculate the pressure. So for this one, we know the given values. Let's write down the given values very quickly. P air is 150 kilonewton per meter square, which is kilopascal. Then the specific gravity of oil is 0.85, and what else? And the depth of each layer, right? So depth of oil was 0.8 meter and the depth of water is 2 meter, and you have to find pressure at the bottom or at point C, right? So what I will do here, I will do one calculation. No, I will do that in next slide. Okay, so let's do the solution. Okay, so if I draw the picture here very quickly, air, oil, water, and the distance for each one is 0.82 meter. So here, since we are trying to calculate the pressure at point C, so PC will be, obviously, we just discussed few minutes ago, the pressure due to air, oil, and water. So the air pressure is already given, which is 150 kilonewton per meter square. Now, for oil, we don't know the pressure. So I will just write down this way, because if you remember, for incompressible fluid, pressure is gamma H, right? Okay. So for water, it will be this one. Okay. So 150, since kilonewton is not the standard unit, I can convert that into Newton per meter square, plus gamma oil is not given, but specific gravity of oil is given. So we need to do one extra step here. Gamma oil plus gamma W is equals to specific gravity. That means instead of gamma oil, we can write down specific gravity, gamma water, H oil, and then plus gamma W, HW. Okay, so let's move to the next slide. PC equals to 150 10 to the power 3. Specific gravity is 85. Gamma water is 9810 Newton per meter square. Yes, meter cube. Okay. So 9810 Newton per meter square. And for water, there has to be 0.8 meter. Okay. And for water, it will be 9810 Newton meter cube 2. Okay. So it will be 150 Newton per meter square, and then 6.67. I already calculated the result, so that's why I'm just directly writing down the value. And for this one, 19.62 Newton per meter square. So altogether it will be 176.29 kilonewton per meter square. So that is the answer for question number, class example 5A. That is the pressure at the bottom of the tank. You see 150 was the only air pressure, but other 26 we got from oil and the water. Okay, now let's work with the part B. They are asking you to determine the pressure head for water and mercury if the gauge pressure is 50 kilopascal at the bottom of the containers. So there are two containers here. This is the water and this is the mercury. Okay, and for both of this tank, the pressure at the bottom is 50 kilopascal. Now they are asking you to find for what height of water column the pressure is 50 kilopascal. In other words, they are asking you to find the pressure head for the water and mercury for this pressure. So we know that the pressure head equals to gamma over H, right? That's what we know. Now all the given values is, we know the pressure, which is 50 kilopascal or 50 times 10 to the power 3 pascal. We know the gamma water, 9.81 kilonewton per meter cube or 9.81 10 to the power 3 kilonewton per meter cube, and gamma mercury is 133. So 133 10 to the power 3 kilonewton per meter cube. Now just from the specific weight, you can see how heavy the mercury is. So for 1 meter cube, the weight of 1 meter cube water is 9.81 into 10 to the power 3. The weight of the mercury is 133 into 10 to the power 3, which is huge. Okay, so you will see that for what column head, you are getting the same pressure at the bottom of each container. So let's work on that. Water, mercury. Okay, so each water equals to P gamma W. So it's 50 10 to the power 3, 9.81, 10 to the power 3, 10 to the power 3, 10 to the power 10 to the power 3. You can cancel that. It will be 5.1 meter if I round that. And mercury will be P three. So 10 to the power 10 to the power 3 got cancelled. It will be 4. Now you can see for water it took 5.1 meter depth of water, while mercury needs only 0.375 or 376 meter to create that 50 kilopascal. Okay, so that's the end of class example 5. Thank you very much. Thank you very much. I will cover the next part of this class in the next video. So you will have 2 videos for this class. Thank you.